Okay, brand new question. Clear your minds. Chemistry student correctly draws and labels a helium atom. An alpha particle is a helium nucleus, so state the difference between the two structures. Well, there's no electrons on an alpha particle, okay? So this is helium. An alpha particle would be just this without the electrons. A nucleus of polonium-218. So 218 is the nucleus number, the number of nucleons. And 84 is the number of protons. Decays by alpha emission. So let's have a look what's happening here. So this side has always got to equal this side. So something plus 4 gives me 218. Well, 214 plus 4 gives me 218. Let's go down the bottom. Something plus 2 gives me 84. Well, that's going to be 82 plus 2 gives me 84. Bro, so I got element X as having a mass number of 214 and a proton number of 82. Now, a short time after, it decays by beta. Now, it wants me to work this out. Now, you wasn't given these values, but you should know just to bring this X down now. So X is going to have 214 and 82. That's what it's going to start with. Now, something plus 0 is going to give me 214. Well, that's 214 plus 0. And then something plus minus 1 is going to give me 82. Well, that's going to be 83 minus 1 gives me 82. Now, the nucleus Y, so this fella, 214, 83, is going to decay by beta emission again. So this needs to come down, this information. Y is 214. There it is. And an 83. Again, it needs to equal. Oh, we haven't going to do any working out there, but we can check ourselves. So 214 plus 0 is 214. 84 plus minus 1 is going to be 83. So we can always check ourselves there as well. Plus, you will get marks for carrying on. This is part of the same question. This, especially down by here, this got to me for a while. It took me a while to get this, but I realized these elements are these ones on this page. So what is element X? Well, here's my table. If I look at element X, it's got, and I want to look at the small number, element X has 82 protons. And the only thing with 82 protons in here is lead. Plum bum. So that's why element X is lead, and it's got a nucleon number now of 214. There it is. And it's soon going to ask me, going to ask me Y. So Y has got a nucleon number of 214 as well, because it was beta decay. And it's got a proton number of 83. So 83 is this one by here called bismuth, Bi, 83. And that's where I got those from. The next question, state which of X, Y, or Z is an isotope of polonium. Well, an isotope is going to have the same small number, so same atomic number. It's got a different number of neutrons. So, as polonium, well, where's polonium? Let's have a look. Polonium 84. I'm looking for 84. Where is it? Is it this one? 84. Well, the only one that's got 84 is that one. So it's Z. And there's my answer. Look, Z. Lovely. Up to the last few pages. Yeah, 3 pages. This one is a beast. So I'm going to try and get this done in 5 minutes. Physics teacher uses 600 identical red dice. Don't know why the colour is important. She throws 600 dice. She removes all the 6s. So there's a 1 in 6 chance here. And then she counts the remaining. In her second demonstration, she repeats her experiment, but now she removes the 5s and the 6s. So now there's a 2 in 6 chance. And in her third demonstration, she removes all the 4, 5s, and 6s. So now there's a 3 in 6 chance. Or you could say a 1 in 2 chance there. Because that's the same as 3 in 6. And she's plotted these. So, this is obviously her first one. Okay? This is obviously her second go. And then when she's removing the 3s, 4s, and 5s, you can see just how short that half-life is. Explain why the teacher chooses to use a large number of dice for a demonstration. Well, Larger samples reduce the effect of random variations with increased confidence. We've had this many times, so the bigger the sample, the more confidence, the less anomalous results you're going to get for 2 marks there. I'm going to leave that out because I'm sure we're going to need it. This question then, oh look, tick boxes again, they're always there. Use only information from the graph to tick 3 correct statements. So line A represents the data from the 3rd demonstration. Well, that is bumf because line A is a shorter, is a longer half-life. Therefore, it's got to be the first one when you've got 1 in 6 probability. So that is nonsense. Line B shows the equivalent of 3 half-lives in 5 throws. Well, we can check that. So line B shows the equivalent of, what was it? Of 3 half-lives in 5 throws. Well, there's the number of throws on the bottom. Is it 3 half-lives? We get down to around about 75. So it starts at 600, then 300, that's 1 half-life. Then it's going to be 150, 2 half-lives, and then, yeah, 75 gets down there. So that statement is correct. There's about 3 half-lives there. Line A represents the isotope that decays at the quickest rate. Line A represents the isotope that decays. Well, that's nonsense, because line A is the line that has got the least decay rate. This is the quickest decay rate, okay? Because here's your activity, or here's your number of dice remaining, is much quicker. It's much quicker, okay? Even like, look at 1 throw and 2 throws, like, it's way down. Line B has an activity that is 1/8 of its original after 5 throws. Well, let's have a look at that. So I've done it here slightly. I don't know. I know it's next to this question, which is kind of throws you. Line B has an activity that is 1/8. Well, to get down to 1/8, so 1/1, then a half-life, 1/2, then a half-life, 1/4, then a half-life, 1/8. It's 3 half-lives. And we've already kind of done this for line B there. It says the equivalent of 3 half-lives. Well, that is 3 half-lives to get down to 8. So, yeah, I mean, that's correct. It's kind of the same as that. Line B shows the equivalent of 3 half-lives. Well, that is 1, 2, 3 half-lives to get down to 1/8. So that is correct as well. I could show you on the graph, but it's pointless because I've shown you once. Line C represents the longest half-life. No, that's incorrect. Line C represents the quickest half-life. Okay, the lower it is, the quicker it is. The teacher suggests to her class that an improved model of radioactive decay would be to include 20 blue cubes along with the 600 red dice at the start. Blue cubes would not be removed during this demonstration, but would be counted each time. So state what physical quantity the blue cubes represent. Well, they're going to represent the non-radioactive material present in any substance. So that's all that would be. For 1 mark, quite a tricky one, and that's why she mentioned the red dice at the beginning. But yeah, if you're not counting them, that means it's not radioactive, so they're not going to decay. State how the presence of blue cubes affect line A on the graph. Well, because they would always be the same number, they would always be 20 higher, and they would never fall below 20 because you could never get rid of those 20 blue cubes. So your dice remaining would never fall below 20, and whatever your remaining dice count is, there's always going to be 20 higher because you've got 20 blue dice now that can never be removed. And then the last one, we're nearly there. A sample of strontium-93 has a mass of 68 milligrams. Calculate the mass of undecayed strontium after 56 minutes. It's got a decay. It's got a half-life of 8 minutes. So show your workings. So I've said it's got a mass of 68 milligrams. It's got a half-life of 8 minutes. Well, let's see how many 8 minutes goes into 56 minutes. So we need to see how many half-lives we got. Well, 8 goes into 56 7 times, so I've got 7 half-lives. Now, I can either do it this way, but I can go 68, half of that, half of that, half of that, half of that, until I got 7 arrows, 1, 2, 3, 4, 5, 6, 7. It's a long process, comes out to 0.454. Or, I can do that 2 to the power 7. Because 1 half-life is 2 to the power 1, 2 half-lives is 2 to the power 2, And how many half-lives you got is to the power of that. So how many 2 times... it's not 2 times 10 to the power 7. It's 2 to the power 7. That's really important. And then a scientist works with strontium-93, which decays by beta. Explain why, for his own safety, he has to store it in a lead box, because lead blocks beta emissions and reduces gamma radiation. This will reduce the exposure to the scientist. Bang on. Thank you, Ron.